Hi, today I am going to be talking about the nuclear bomb. Just want to give you a quick rundown before I get started. I'm going to start off by just giving some basic definitions of some concepts that I find important in order to understand what is going on throughout this whole process. After that, after covering just the basic background info on these definitions, I'm going to move on and just talk about how engineers and scientists separate uranium isotopes from one another, and how this is accomplished in power plants. And lastly, I'm just going to give an example which shows how powerful the nuclear bomb is and just talk a little bit more about that. All right, let me begin by just stating the obvious. Nuclear bombs are weapons of mass destruction. I feel like that is pretty much well known throughout all of society. They harness the forces that hold the nucleus of an atom together by using energy released when the particles of the nucleus, the neutrons and the protons, are split or merged. So since we're talking about split or merged, now let's jump into the basic definitions that I want to cover. So there are two ways that energy can be released by an atom. There is nuclear fission and there is nuclear fusion. So fission and fusion. Tongue twister. So nuclear fission occurs when the nucleus of an atom is split into two smaller fragments of a neutron. So this method usually involves isotopes of uranium or plutonium. So for example, this is used in the process of making the atomic bomb. Nuclear fusion occurs when two smaller atoms are brought together, usually hydrogen or hydrogen isotopes, to form a larger atom. So for example, this is how the sun produces energy. All right, so now that we've covered the definitions of nuclear fission and nuclear fusion, let's dive into how uranium is separated in nuclear power plants, why this is the case, and clarify the process to the best of my ability. So the video we watched on Blackboard talked about two very similar variants of the isotope uranium. Or the atom uranium. There were two different isotopes. So the engineer from the YouTube video mentions how uranium can typically be found in the form of uranium ore and contains two isotopes, uranium-238, which has 146 neutrons and 92 protons, and uranium-235, which has 143 neutrons and 92 protons. So let's discuss the differences between those two. Uranium-238 is more plentiful in nature than uranium-235, and uranium-238 has a heavier weight since it is carrying 3 more neutrons than uranium-235. Uranium-235 can be found in about 1 out of every 140 naturally occurring uranium atoms, and it can easily be split to cause a chain reaction process. So this is the isotope of uranium that is used in the process of making the atomic bomb, or this is what is separated out in power plants in order to make that atomic bomb. So, for example, let's just say you start with one atom of uranium-235. Its low-charged neutrons can go through the process of fission and then impact two atoms. So, say you start with one. So this one can be split into two. It can break off neutrons and it can go to two. These two can break off to 4, the 4 to the 8, the 8 to the 16, and so on. This process just can continue on until there's no more to be split. So uranium-235, as mentioned just a second ago, weighs slightly less than uranium-238, which makes it easier, not easy, but easier for scientists and engineers to be able to separate these two isotopes from one another. What blew my mind from the video was the fact that it took nearly 4,000 stages to enrich 3% uranium-235 to 90%, which just proves that this is such a complicated and very methodical process. All right, so in order to create the first ever atomic bomb, it required a diffusion plant, which was 40 acres, and in those 40 acres it had 100 miles of piping inside, which is crazy to think about how long this piping had to be in order to get this process complete. But now I want to talk about how a centrifuge would potentially speed up the process and just talk about what it is. So a centrifuge has a rotator, and as it spins more rapidly, the uranium-238 would be pushed towards the edge of it. It would be in a cylinder type thing. Here's the center, and as the rotor spins, the uranium-238 would be found on the outside, while the uranium-235 would stay closer towards the center. Then the enriched portion can be sent to another centrifuge, so just kind of like centrifuge, 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 just kind of in a line, and it can move from centrifuge to centrifuge in order to get more enriched as it goes on. So in order to specifically pull out just the uranium-235 and leave the 238 behind, because that's not what they want. With this, the amount of enrichment is only a fraction of the percent, so it would take roughly about 60,000 centrifuges in a plant in order to be able to accomplish this task, which is crazy. You go from 40 acres and 100 miles of piping to 60,000 centrifuges. So these types of plants use only about 4% of the energy as a gaseous power plant. And although it uses less energy, it requires such precision that is hard to perfect unless you are someone who is highly specialized in this field. With even the slightest defect, as the man mentioned in the video, the rotor could spin itself to pieces. Also, something else that was mentioned in the video, we're very lucky that this is the case, so that this kind of information and technology as to how to build this does not fall into the hands of a person with malicious intent. I don't know about you, but I'm fine not knowing how to create and conduct this process myself. I'm more willing to leave it in the hands of the experts because I, prefer not to have weapons of mass destruction casually sitting around my home, as I would assume you would too. So just to recap this section of my presentation, when a single free neutron strikes the nucleus of an atom of radioactive material, such as uranium, it knocks 2 or 3 more neutrons free, which is the process of 4,000 different stages. So then energy is released when those neutrons split off from the nucleus, and the newly released neutrons strike other uranium nuclei, splitting them in the same way, releasing more energy and more neutrons, which is the chain reaction effect that I mentioned previously. And yeah, all right, so now I'm going to finish up my presentation just by talking about an example of a nuclear bomb, an atomic bomb that we saw. So the first ever atomic bomb used utterly destroyed Hiroshima, and that was at the end of World War II. This bomb it contained about 60 kilograms of uranium-235, and only about 600 grams or 0.6 kilograms underwent the process of fission. So 60 kilograms, but only 0.6 kilograms underwent the process of fission, yet this was an extreme explosion. So with this explosion, it was equivalent to about 13 kilotons of TNT. To me, that's mind-boggling just to think how big that explosion must have been. I'll drop some pictures that I found online when I was just looking up this process right here so that you can I'm sure you've seen it, but so you can see the things that I saw. So just to put that into perspective, it takes only about 0.005% the amount of uranium-235 to cause the same size explosion as 13 kilotons of TNT. That's crazy. So I just want to touch on the structure of the bomb before I finish up. So the structure of the bomb used at Hiroshima, 40% of the uranium-235 was put at the tip of the bomb, which was at the end. And then at the other end, there was a conventional charge that was used to push the remaining 60% into the target, or the other 40%, which triggered the explosion. So they separated the two parts of uranium because they knew when they came together, it would cause the giant explosion. All right, well, that is all I have for my presentation today, and thank you for watching.